Hello and welcome. I continue my work through the huge pile of hardware which I got donated from Stibor last month. And today I would like to take a look at this 486 mainboard. Stibor wrote a short message here that this board doesn't post and that it is a 486 mainboard. Hippo 15 doesn't have anything to do with Hippopotamus, but is a model name of a manufacturer, Octek. They always named the mainboards after different animals like panther, jaguar, fox or pony. Actually a funny idea, and Hippo was not an exclusion. Let's see if we can revive this mainboard today. So, this is obviously mainboard, which is based around UMC UM8881 chipset, which was one of the fastest, and most of the 486 benchmark records were made using mainboards with this chipset. And we are in luck, since Octek was obviously very smart and didn't use neither a stupid Dallas RTC module nor a barrel battery. Instead, they went with a CR2032 cell battery, saving this board from any corrosion damage due to leaking electrolyte. That was actually very progressive for a 486 board. And also another sign of a progressive and a very late 486 board is the integrated Super I/O controller with already two IDE ports for up to 4 devices, as well as the usual suspects: floppy, parallel port, joystick port and 2 serial ports right below the AT power connector. The board requires 72-pin memory modules, and you can install up to 4 times 32 MB of FPM memory modules with up to 128 MB of total memory. However, if I remember right, this UMC chipset can't cache as much memory, so it wouldn't make so much sense. However, I might be wrong about this. Next important point, and probably the most important, which CPUs are supported. Well, this mainboard supports any 486 CPU which existed on the market back then. Also the AMD 5x86 at 133 MHz or even overclocked. All that thanks to the onboard voltage regulator, which provides the power for all 3 volts to 5 volts CPUs. So, all in all, a really nice board and a very good base for a 486 retro machine. With onboard I/O controller, the PCI slots where you can install fast, cheap and easy to get PCI graphics cards, as well as the ISO slots for sound cards and all the other existing retro expansions. This board is maybe not the cheapest one, but at least judging by the features it provides, it should be a very nice option, and it would be great if this one would stay with us a little bit longer. Stibor wrote that it doesn't post, and I trust his expertise, but let's see how bad it is. First, what instantly jumped into my eyes on this board is that the cache modules are probably in the wrong sockets. This board has 128K of cache in 4x32K modules and 132K tag chip. And they are all inserted into the lower, narrower sockets. As you see, the upper sockets are wider, they optionally accept larger cache ICs, but you also can install smaller ICs into them. Out of experience, I know that such larger sockets have to be populated first. I might be wrong about it, but now we will need some documentation. Especially when dealing with 486 mainboards, it is really important to start with searching for documentation. This platform reached the extreme when talking about the jumpers. Later, the manufacturers understood that the crazy amount of jumpers started to be annoying and a very common source of errors. So for the Pentium motherboards, a lot of settings went into the BIOS and could be set in software. But for the 486 we often had to deal with dozens of jumpers, and this Octek Hippo 15 was not an exception. Just as always, the best point to start searching for the mainboard documentation, BIOS and images is the Ultimate Retro project. And for this board we are especially lucky, since there are even multiple manuals available. I printed one because I always like to have it printed and stored together with the mainboard. And here we have all the memory and cache settings, all the jumper settings for the different CPUs, and here are voltages. Let's go back to the cache settings once again. Let's take a look at the schematics first. Let me rotate it so it is in the same orientation as the mainboard on the table. Yeah, Here you see that the bank 0, which usually has to be populated first, are the longer sockets, and bank 1 are the shorter ones. So currently the cache ICs are inserted into the bank 1, which is probably wrong. Yeah, and as you see, we have 128K divided in 4 times 32K ICs, and they all should be in the bank 0. Bank 1 should have no ICs in it, only the tag chip should be in the lowest socket. So those longer sockets should be populated first, and those 4 ICs must be moved up there. The tag IC will have to remain where it is. Let me remove the ICs. By the way, here you see the number 1256. It is 32 kilobyte SRAM chip, and my mnemonic is 1 for 1000 times and 256 for, well, 256 bits, which is 32 kilobyte in other words. Also interesting number here is -15 in the end, which stands for 15 nanoseconds latency, a quite fast SRAM, which should easily run even at 50 MHz frontside bus. That is really cool for overclocking on this board. However, today I don't think that I will come to overclocking, since I simply don't have any fast 486 CPUs at hand. The fastest I have is an AMD DX280 MHz, which won't be very exciting on this board, I guess. Well, of course, in case that this board will work at all. So the cache ICs are now removed. The only one left is the lowest one, which is a cache tag chip. I will add some dioxide. Always do that if you remove the ICs anyway. That can help to avoid some strange issues hunting. Now the question is how to insert such chips properly. As you can see, the sockets are slightly longer than the ICs. That is not a problem. This board is wired in such a way that it can accept shorter ICs in these longer sockets. However, when inserting, pay attention to put the ICs into the end of the sockets like this. Here you can see the orientation notch on the IC, which has to go into the same direction as the notch on the socket, but the IC has to be aligned with the end of the socket. And all the other sockets will be populated in the same way. Now it's time to set the jumpers, but to do so I will need to know which CPU I'm going to test this mainboard with. I have some 486 CPUs in my collection, and I think that I will go with this one. It already has a cooler glued on top, so I don't need to take care of that, and it is an Intel 486 DX2 with 66 MHz designed for 5 volts. And now, where I know which CPU it will be, I can set up the jumpers. However, I will not put the CPU into the socket yet. For now, it is just enough to know that it is going to be an Intel DX266. And before I put the CPU into the socket, I should check the voltage first to avoid any damage to the seldom piece of silicon. And therefore, I will have to refer to the manual and set the jumpers accordingly. And here you can see what I meant. This board has already such a crazy amount of jumpers, and this is just a part which is responsible for the CPU. There are other jumpers for cache, voltage, frontside bus, I/O controller, etc, etc. Okay, meanwhile I think that I set all the jumpers accordingly, and funny enough I think I know which CPU was running in this board before. Or at least for which board it was configured. Do you remember this cool UMC CPU which Tibor donated in the same package as this mainboard? Well, regarding to the jumper settings, as they were previously set, this mainboard was configured to run this CPU, and one day in the future it would be great to try the CPU in this board indeed. I find the idea to have a UMC CPU in a UMC board quite cool. Okay, I think that I have now all the jumpers set properly. The frontside bus is set to 33 MHz and the multiplier is 2 as required by this DX266 CPU. However, the multiply jumper actually shouldn't play any role, since this CPU has the multiplier hardwired internally and it doesn't matter what I set up on the board. Another interesting and quite unusual thing about this board is that it seems to have some kind of voltage auto detection for 3 and 5 volt CPUs. To be honest, it is the first time for me to see something like that on a 486 mainboard. Okay, now I actually could put the CPU into the socket, but before I do so, let's first check the voltage. Therefore, I will insert a wire into the VCC pin of the socket. Furthermore, I will add another wire to the clock pin, so we can measure if the required frontside bus clock arrives at the CPU at all. Off camera, I already tested the AT connector for shorts and it looks good so far. So, first try. Nothing exploded so far, that's a good sign. The voltage seems to be at almost 5 volts, that's okay. Unfortunately, the frontside bus clock is either too high for my multimeter or is not arriving at the CPU. My multimeter can usually measure only up to 25 MHz and with 33 MHz this is just too much. Okay, I will reinsert the cable into the ground pin now, since I will need it for the oscilloscope. And here we go, perfectly fine 33 MHz. So, the voltage seems to be okay and the clock arrives at the socket as well. I guess it is time to insert the CPU. The 486 socket has no insertion key, which would protect you from wrong insertion, so always search for such a cut corner on the CPU and insert it towards the corner where the lever is mounted. And just as always, let's add the post analyzer and the PC speaker. So I hope I didn't forget anything. Let's start! And the system seems to be completely dead. No numbers are running on the post analyzer and there are no beep error codes. Usually we should see some numbers and the board should complain about missing memory, but nope, it is stone dead. Just as I like it to be. It would be really boring otherwise, don't you think? Well, in the last video I showed you already my prototyping board, which I use not only for prototyping but also for testing the signals. Let's see if there are some activity on the address bus at all. And nope, absolutely dead and buried. You know what? Let's measure once again the voltage on the CPU. Whoa! Would you look at that? 2.4 volts is definitely too low. But did I measure it on the wrong pin previously? Well, that would be stupid. But yes, obviously the CPU doesn't get enough power. Okay, I looked at the power supply a little bit closer, and as I already said, this is the first time I see a voltage auto detection circuitry on a 486 mainboard. But it is really complicated to follow. Let's see. This is the main power transistor, which provides the power to the CPU. This transistor can be powered by 5 volts and 12 volts from here, which is currently hardwired to 5 volts. So these 5 volts go to the transistor, and dependent on how wide it is opened, it delivers voltages up to 5 volts to the CPU. The question is, who decides how wide is the transistor to be opened? This is partially done by those smaller transistors here, the 5 of them which are located around the jumper header, where the desired voltage can be set up. All this stuff is connected to this differential comparator, which compares the output voltage with the desired one, which was set on the jumpers and all the resistors around it. This whole construct is really weird and not quite easy to analyze. In such cases, many people on the internet start to suggest to recap the board. And to be honest, I'm not a friend of recapping the hardware just because I can. I would suggest to change the capacitors only if there are obvious reasons for that. For example, if they are damaged, blown or obviously leaky. But here the caps look as good as new. The Rubicon capacitors are already over 25 years old and looks like they will serve even longer. Anyway, I have no reasons now to suspect those capacitors. They look good to me. So the first thing to check in such cases is the power transistor. These guys can get quite hot and usually get damaged first. So let's just check the resistance between the pins. Here we have 144 ohms, and that looks quite low to me. Here are 155 ohms, this is also very low. Oh, and between these two pins we have only 10 ohms. Let's take a look at the datasheet. The transistor is an NDP603AL and is an N-channel field effect transistor, and it has the gate on the left pin, the drain in the middle and the source on the right. So I just measured the low resistance of only 10 ohms between the gate and the source. That cannot be right, but I also can tell now if the transistor is bad or something around it in this weird voltage auto-detection circuitry. So I will have to remove it from the board and measure it separately. Desoldering and soldering power transistors can be tricky sometimes. As I told, such guys can get quite hot, so they usually are equipped with additional heatsink or simply soldered to a big copper plane on the PCB, which would absorb the heat, like on this mainboard. The problem is that you need a powerful soldering iron to get it off the board, otherwise the big copper area will cool down the solder faster than you can heat it up. I set my soldering iron now to 400 degrees, and hopefully this will be enough to get the transistor from the pad. And it looks good. The solder melts so far, and I will simply lift the transistor on this side. Now the pins can be desoldered, and for such simple case you don't always need a full desoldering station. Sometimes such a manual solder pump is more than enough. But always add some fresh solder to the joints, this will simplify the process quite a lot. Okay, the transistor is desoldered now. Let's check the resistance. This looks much better. We have resistance in kilo ohms and not 10 ohms like before, so it looks like the transistor is dead indeed. And yeah, there are only 10 ohms between the gate and the source pin. That is far too low. Let's see what the tester says once again. Yes, also here, part unknown or damaged. The transistor is obviously dead. As I already mentioned, the model is NDP603AL, and I have to look in my spare parts if I can find something to replace it. So, unfortunately, I didn't find the same one, but I found this CEB703AL SMD FET. I compared the datasheets and they have the same pinout, but the 703, which I found, is even a little bit more powerful and is rated for up to 30 volts and 40 amps instead of 25 volts and 30 amps as for the old 603. That is even better, since it should stay a little bit cooler, otherwise they should be pretty much the same. It is not new, I desoldered it from another physically damaged mainboard in my spares box, so this could be broken as well. Let's test it first. On the tester there is the spares area, which is especially made for SMD parts. Yeah, N-channel enhanced MOS. The pin on the pad 1 is source, the pin on the pad 2 is gate, and the pin on the third pad is drain. That is right, and what we need. The transistor seems to be good. There is one thing, however. The old 603 was a through-hole component, but the 703 which I have here is a surface-mounted one. But this is not a problem. I'll just straighten the pins and it should work as well. One remark maybe, you probably noticed that the replacement transistor doesn't have the middle pin, like the original one. Well, that doesn't matter, since the middle pin on this model is connected to the cooling notch on the back. And as you see on the copper area on the PCB, it is connected right to the middle pin as well. So when we solder the cooling notch to the plane, it doesn't matter if the middle pin is soldered or not. Now, how to solder such a transistor with a normal soldering iron? Well, no electronic parts like heat, and if you can avoid it, do so whenever possible. So in such cases, I again set the soldering iron to 400 degrees and heat up the copper area with some solder on it first. And when the solder is really fluid, I press the transistor very fast into it, continuing to heat up the excessive solder around. The cooling notch underneath the transistor will heat up very shortly, and it will stick to the plane underneath. As you see, the transistor will be not overheated at all, since I even still can hold my fingers on top of it. Afterwards, the pins can be soldered from the other side as well, and always clean everything with some APA afterwards. Let's check the resistance once again on the board. It is multiple kilo ohms, very nice. Let's check the voltage once again. Yeah, 5 volts, but we had it already last time. So let's put the CPU once again into the socket and the post analyzer and see what we get. And again, nothing happens, but I think that we are a step forward. The old transistor was definitely faulty. All what I can say now is that the new transistor doesn't get warm. Let's go back and measure the voltages once again. On the drain there are 5 volts, this is the input, and on the source, which is the output and which goes to the CPU, we have only 2.4 volts. The jumper is currently set to 5 volts without auto detection, so we should get on the source 5 volts and not 2.4 volts. Okay, I looked more closely on the circuit and I don't know how I could overlook that. Take a second and look if you can spot the problem in this picture. I'm sure you could. But obviously I needed some time and a better light to see the tainted color of that fuse resistor. That doesn't look good at all and is located directly between the source pin of the power transistor and the CPU. So I desoldered the fuse and as you can see it looks burnt and the color code rings are hard to identify. However, on the other side you can hopefully see that there is a black ring followed by a brown one and 2 silver rings. As you can see, this fuse should have almost no resistance at all. Let's see what the tester will say. Wow, 6 kilo ohm. That explains the voltage drop, I guess. The interesting question is always how that can happen. This fuse's job is to protect the circuitry from overcurrent. And in our circuitry both the fuse and the transistor were faulty. How that could happen? I have multiple possible scenarios. First, for example, by inserting the CPU the wrong way around, the VCC pins could be directly connected to the ground, which would pull unlimited current through the power transistor. In such case, the fuse should blow up and limit the current. The second explanation could be that someone tried to overclock the CPU and drew too much power through the fuse. As far as I can see, it is a 5 watts fuse, which means that at 3.45 volts it can stand the current up to 1.4 amps. Due to the datasheet, the 486DX4 would draw up to 1.2 amps at 120 MHz. And with a little bit of overclocking, the 1.4 amps are not very far. Also, if someone would drive a 3V 486DX4 CPU with 5 volts in this board, the maximum fuse current of 1 amp would be already reached at 100 MHz. However, both possibilities don't explain why the transistor didn't survive. So another one could be that the transistor died and sent a short high current peak through the fuse, which blew up and protected the CPU. I will leave it up to you which theory you like more. The point is that the transistor and the fuse were both dead. Now I could simply replace the fuse by a jumper wire, but I would like not to risk too much. Unfortunately, I didn't find a fuse similar to the one which was used previously on this board, but I found this 3 amp fuse in my spare parts. It is a bit too forgiving for a 486 and I should search one which is more like 1.5 amps, but for now it is better than no fuse at all. Okay, the fuse is installed and we have continuity. Looks good so far. Time for another try. The CPU is back in place, as well as the post analyzer and the PC speaker. The voltage selection jumper is now set to 5 volts without auto detection. I don't trust that one yet. I will need the multimeter again to measure the voltage. Let's turn on the old lady. Ah, finally, there is a beep and the post analyzer reports some numbers. That's a good sign. And the speaker continues with long beeps, which is memory error. That's right, since we have no memory installed yet. First, let me check the voltage. Yep, 4.89 volts. It's not perfect, but good enough. That is great, and before we continue, let's turn off the power and set the voltage selection jumper to auto detection. Yes, it seems to work as well. We are getting again about 4.9 volts. The auto detection should normally switch automatically between 5 volts and 3.45 volts, I think. But I will not try a 3 volt CPU now. Instead, let's repeat the game once again and set the jumpers to 3.6 volts without auto detection. The DX266 needs 5 volts and will probably not initialize at 3.6 volts at all, but I should be able to measure the voltages at least. Oh wow, the CPU seems to be alive. That was unexpected. Let's see what the voltage says. Yeah, we are getting 3.6 volts indeed. It surprises me that the CPU is starting at all. But I think that even if it initializes, it will not run stable at such a low voltage. That is great. The CPU power supply seems to be up and running again. Let me set the voltage jumper to auto detection again and see if we get an image on the display. Therefore, I will of course need some RAM. I will install 8 MB of FPM RAM. By the way, most of the 486 mainboards don't work with IDO RAM properly, so always pay attention to use FPM modules in such systems. Of course, I will need a graphics card as well. This PCI S3 Trio 64 should do the job perfectly. So, I added the keyboard as well, and I will plug in this compact flash to IDE adapter with DOS and some software on it, in the hope that the system will be able to boot into DOS at all. So let's start. Yes, we have an image. Hippo 15 BIOS from 1995. The detected CPU is the 486DX2 at 66 MHz, that's right, and also 8 MB RAM is true. Yes, CMOS checksum error is due to empty battery on the board. I didn't change it yet. I will not make any BIOS setting except turning on the auto detection on the IDE controller to get the compact flash card auto detected. All the other settings shall remain in defaults for now. And yes, my 500 MB compact flash card was detected. And what shall I say? It's booting into DOS. Let's see what system information says. Yeah, everything seems to be okay. Benchmark is at 144 points, which are normal for the CPU. And can I start Doom? Yes, I can. It seems to be working so far. Of course, I didn't try all the features now, but so far it looks really good. And if Doom runs, I consider a mainboard working. Well, jokes aside, but it is a superb progress, I would say. So, the problem on this mainboard was obviously some damage in the power supply circuitry for the CPU. These two guys left the world of the living and tried to pull this mainboard into the eternal darkness with them. But today we managed to resurrect this great mainboard and hopefully it will serve many more years. By the way, I know that a lot of people will complain that I should recap this board and they always recap everything they get in their hands and, well, I don't. It costs a lot of time and it is absolutely not necessary in the most cases. I desoldered off camera this cap to show that it is absolutely fine. Even after over 25 years, it is still in perfect condition and I see no reason to change it. And at this point I would really like to thank Tibor once again for his great donation. I'm very glad about having this board in my collection, since, as I said, such later 486 boards, which were built around UMC chipsets, are really beloved in the retro community for incredible overclocking abilities and wide support of CPUs. And speaking of CPUs, this video got already quite long, but I would like to use the abilities of this board and run some interesting benchmarks in my next video. Today I used such an Intel 486DX266 CPU for testing, and in my next video I would like to compare it with another exciting CPUs, and super rare CPU which I got donated by Tibor together with this mainboard. The UMC U5S at 40 MHz. I'm very curious how this one will run, and it is especially cool to have a UMC CPU in an UMC chipset based mainboard, don't you think? And to keep the benchmarks even more interesting, I sorted out some exciting competitors which I could compare clock for clock. There is this AMD 486DX40, a Cyrix CX486DX40, also a very interesting CPU, completely designed by Cyrix and not just a copy of the Intel CPUs like AMD did. And last but not least, the genuine Intel 486DX50, which I would like to downclock to 40 MHz as well, to see how all those CPUs will run against each other at the same clock. Of course, except the DX266, which will serve as a reference. So, if you are interested in these benchmarks, consider to subscribe if you didn't already, and keep an eye on my channel. And for this video, I hope you enjoyed this repair. Just as always, I'd be glad about your feedback, and for now I say thank you and goodbye.